In this video, I'm going to talk about LDP session protection. LDP session protection is a feature that can protect our network from for example, flapping links. The flapping of links can have several causes. I don't want to talk about that causes, but you know that flapping links means that the link that is going to down state and again to up state, again down, again up, and this is the flapping link. And flapping link do have an important impact on the convergence of the network because the IGP adjacency and the LDP session are running across the link. They go down when the link goes down and they go up when the link goes up. This is unfortunately especially because the link is usually not down for long. The impact is pretty severe though, because the routing protocol and LDP can take time to rebuild the neighborship. Again, LDP has to rebuild the LDP session and must exchange the label binding again. Okay, to avoid having to rebuild the LDP session altogether, you can protect it, okay, with the LDP session protection. Let's talk about these. Look at this picture, for example. This is a small scenario. I want to use this scenario for MPLS LDP session protection. Assume that we enabled MPLS on all of interfaces of this scenario. This is MPLS enabled interface and also other interfaces. This is MPLS enabled, means LDP enabled. Okay, we have LDP enabled on this in this interface, and again here LDP, and here and also in R3's interface. Now you experience LDP peers or LDP neighborship between the R2 and R3, also between R1 and R2 and R1 and R3. Okay, but we want to focus on the link between R2 and R3. You know that when the link between R2 and R3 goes down, for example, it failed, okay, the LDP neighborship and also the OSPF neighborship, routing protocol neighborship, go down into the down state. And we don't have connectivity between R2 and R3. In that time, when a packet receives to R2, because the link between R2 and R3 now is in down state, R2 forward this packet to R1 with label received from R1, and then R1 send this packet to the R3, okay, and finally with the R3 the packet is sent to the destination. For example, assume that we have a destination, look quad 3, okay, quad 3, the IP address of the loopback interface. Okay, because the link between R2 and R3 now is in down state, the packet goes from R2 to R1 and then R3 with label. Okay, this is the status, this is the action when the link between R2 and R3 goes down. And then the link, because the link is flapping, link is in up state after some second. Okay, now R2 should first establish OSPF or other routing protocol neighborship, and then after OSPF neighborship is coming to up state, LDP session can be established. And after LDP session establishment, label binding message can be exchanged between two routers. Okay, but we have a problem here. What is the problem? When the link is coming to up state and then OSPF is in up state, means that OSPF neighborship now established between R2 and R3, and then LDP neighborship established between R2 and R3, sometime is required to sending labels from R3 to R2. This means that according to the routing table of R2, the next hop now is R3. According to the routing table of R2, the next hop is R3, okay? Because the link now is in up state. But the problem is the label that should be received from R1 doesn't receive, okay? Or an R2 cannot send the traffic toward R3. And also don't use, and also the R2 doesn't use the link between R2 and R1, or doesn't send traffic to R1. Why? Because R2 in this time knows that the next hop is R3 and it needs to the label of R3, but label of R3 reaches to R2 after some second. In this fashion, R2 should drop the packets until the label binding between R3 and R2 is after some time exchanging, and then R2 can send traffic to R3. This is our problem. And when the link or the line is in flapping state, after label binding received from R3 use these links. But now the link again goes to the down state. And in the down state, R2 understand the next hop now is R1. And should the R1 labels, okay, R2 has R1 labels and can send traffic. But after some second, this link goes again to up state. And then R2 needs to use the R3's labels. And in another time, again, it should drop the packets to the time that R3 send the labels to the label binding to the R2. And this is the problem we experience in real world, because in real world, in some time you will experience the flapping links. What is the solution? What is the solution to the flapping links? First, you should remove the flapping links. You should check the links, and if you understand some links physically or for other reasons goes up and down state, you should check it and find it, and maybe to need to replace it, or maybe you can correct it. It is not our problem. We are MPLS engineers, not the layer 1 engineer, okay? In MPLS, you can use MPLS LDP session protection. What is the session protection? Look at here. You know that for this time, when the link between R2 and R3 is in up state, we have neighborship, local neighborship between R2 and R3, and also between R2 and R1, and also between R1 and R3. All of these sessions are local LDP sessions that you know, and you experience this type of session between the connected networks, okay? When the links goes to down state, and then the traffic forwarded from other link, and then again when the link coming or going to the down state, you have a problem. The problem is the labels R2 learned from R3 now is out, now is removed from R2's, okay? And after the links comes up back again, you need the labels immediately, okay? The solution is that we can enable an LDP neighborship between R2 and R3 from other links, a targeted LDP session. You know the targeted LDP session. Let me show you, for example, with another color. I can configure a targeted LDP session between R2 and R3, for example. This is the targeted LDP session here. And then, for example, between the